All semester, we have explored slope, and in particular, its relationship to the graph. In this, we're going to talk about the first derivative and its relationship to the graph, very specifically as far as how can we use the derivative to look at the original function. Because this class focuses on applied math problems, often in life we're looking at optimization type problems. When is something reaching a maximum or a minimum? So first let's look at this graph, and I said please find the max and min values of the function. So what we have right now is we have this point, which is a max of 3, 5, and this point over here, which is a min of 6, 2. Okay. We also have these endpoints over here that could also be max or min. So there's a difference between absolute max and a local max or min. So the difference between an absolute and a local, and we'll talk about those later. One thing in particular I want you to note is the slope. So this is the graph of f, but the tangent line right here, the slope of that line is f prime, and f prime equals 0. Slope is 0 right there, and if you put a tangent line right down here, the slope of that is 0. So there's something to be said that when the derivative or the slope is 0, we know that there's a max or min. Okay, let's look at the relationship between the derivative and the original function. So we're going to look here, what does the derivative say about the original function? Now remember, the derivative is the slope. So what does the slope say about the original function? Okay, so let's look over here. Let's see what's going on. From A to B, you can see the slope is positive, and let's write that down. So from A to B, the slope is positive. And if we trace the graph, the function is increasing. So the function f is increasing. Okay, now from B to C, it looks like the slopes are negative here, and the function is decreasing. Okay, so then the function slopes negative, and the function is decreasing. Okay, then from C to D, the slopes are positive here, and the function is increasing. Okay, so the slopes are positive again, and the function is increasing. Okay, now let's look at what happens at B and C. So at B, we have a tangent line here, and what is the slope of that tangent line? 0. And at C, we have a tangent line, and the slope of that is 0. So right here in between these points, so when you go from an increasing to a decreasing, in between there, the function has a max and the slope is 0. And when you go from decreasing to increasing over here at C, you have a min and your slope is 0. So that is what I'm talking about in this chart over here. Okay, talking about that chart over here. Let's put it over here. Okay, we have our derivative and our original function. So when the derivative is negative, the original function is, or positive, the original function is increasing. When the derivative or slope is negative, the original function is decreasing. So if you're positive, you're going up, you're increasing. If you have a negative slope, you're going down, you're decreasing. What happens when your slope is 0? When your slope is 0, like at B and C, you're either going to have a max or a min. And you're not rising or falling, you're doing neither. You're neither rising nor falling. What is the difference between absolute, local, and global in reference to maximums and minimums? Well, by definition, the number f of c is a local max if it's the highest value when x is near c. There's language right here, near c. It's a local min if it's the lowest value for all the nearby values when x is near c. So my question next is, what does near mean? What does near mean? And the idea behind this is neighborhoods. Or locally. Okay, so looking at the graph to your right here at x equals 4 is a local min, x equals at 8 is a local max, and x equals 12 is a local and an absolute min. So what does it mean to be locally local minimum or the locally min? What that means is in a neighborhood surrounding that area, it is the lowest point. I tend to think about people. So there are people that are cool, they're locally cool, but then when you look globally, in other words, they're locally in their little neighborhood, they are cool right here. But when you look at the world at large, they are not as much because there's somebody else over here more so. And that's the difference between locally or neighborhood having the lowest or highest point versus globally or absolutely. So some graphs won't have an absolute max or min. This one doesn't. It has a local max right here, but it doesn't have an absolute max unless you count this point over here and say that it stops right there. That could be an absolute max. But if that graph keeps going, okay, there's an arrow, this graph will not have an absolute max. If we consider a graph on a specific interval like A to E, and we're looking for the max value, the min value, or an extrema, which is either a max or min. So that's an important terminology to add to your notes is extrema. When we say find the extrema, we're talking about find the extreme values, find the local max, the local min, the absolute max, the absolute min. And what does that mean? So now I want you to take a minute, draw the graph on your notes, and then tell me these items over here on the right. Where is the absolute max? Where is the absolute min? What is the local max and the local min based upon this picture? So give yourself a couple minutes and write that down. Okay, so the absolute max would have to be the highest point that the graph achieves. And we're going to assume that the graph stops right here because they're not saying that it continues and right here. So what is the highest point? It would be right here. Note that the slope of the tangent line is 0 there. And so the absolute max occurs at x equals d. Where does the absolute min occur? It looks like, even though this is a min here at E, Notice that the slope here is 0. This over here at A looks like it's lower to me. So I would say x equals A is the absolute min of this graph. Okay, where is a local max? Well, a local max, we have one here. At B, also note that the slope is 0. So local max is in a neighborhood, local equal, so that is B. Also D. And also, well, we don't have that other one labeled, so I guess that's it. Local min would be E and C. Wouldn't you agree that right here at C is a local min? Now, let's talk about the slope at C, the tangent line. Is the tangent line right there? It's kind of representative of negative slope. Or is the tangent line right there? Or is the tangent line right there? Remember, we called this the teeter-totter effect. That is a technical term. And what that means is we can't figure out really what the slope is. Whenever you have a kink in your graph, when you can't figure out what the slope is, so the derivative does not exist. The slope does not exist. It's undefined. We don't know if it's negative, positive, or 0. Okay, so we danced around this, but let's talk about what a critical number or a critical point is. Given any function with a value c in the domain, that's any c, that number is called a critical number or a critical point if one of the two things happen. If it is when the derivative equals 0, or if it's when the derivative does not exist. Those are two really important values. Why are they so important? Well, when the derivative equals 0, that means the slope is 0. And what occurs when the slope is 0? Look at this graph to the right. When the slope is 0, you have a local min, or a local max, or maybe just a change in concavity. So these points matter. Also when it does not exist. Down here, we also have a derivative that does not exist. Is the slope negative or positive or 0? Right here, we have a slope that does not exist. So, and right here, we have a slope that does not exist. So, DNE, DNE, DNE. So, whenever, note down here at the bottom, max and mins occur only at critical numbers. So if you're looking for the max or min of a function for whatever reason, you're trying to find out when your cost is maxing out or when you're making the minimum amount of value and you just want to find max and mins, you know that they only occur at critical numbers. So if you can find the critical numbers, then you'll know where those max and min occurs. But the converse, you have to be very careful about this. Just because it's a critical number does not mean that a max or min will occur. You still have to have some further information. So, what do you do to find max and mins? Find the critical numbers. On what are their critical numbers? These two things here. When does the derivative equal 0? And when does the derivative not exist? This is going to be our first example, and we are going to examine the function f of x equals x cubed plus 2x squared plus 1. Now, we already have a working knowledge of what this function could look like. From earlier in the semester, we talked about the end behavior. It will probably look like, since it's a cubic, the arms do different things. So it could look like this. And there could be up to 3 zeros, but let's say we know some calculus to examine it further. So we're going to find the derivative of the function. We're going to find the critical numbers of the derivative, which, if you recall from the prior slide, that's the zeros and the d and e. Find the intervals where the derivative is positive and negative, and then we're going to answer some questions. So let's look first at the derivative of the function. So our derivative is 3x squared plus 4x. Now we need to find the critical numbers. So the critical numbers are two things. They are the zeros of the derivative and the d and e. Okay, there are no places where the derivative does not exist. That function 3x squared plus 4x always exists. So we just need to look at the zeros. So we have 3x squared plus 4x equal to 0. We can factor out an x. We get 3x plus 4. So we get x equals 0 and 3x plus 4 equals 0. And that gives us x equals negative 4/3 when we solve that. So now we need to look at some things because we know number 3 says, so we've done 1 and 2. Number 3 says find the intervals where the derivative is positive and negative. So intervals. Well, if you think about a number line, put it over here. Think about a number line. We now have, on our number line, we have negative 4/3. So it's between -1 and -2. And over here we have 0. So because we have broken the number line between these two numbers, we have the part of the number line before negative 4/3, then we have negative 4/3. We have the part of the number line between negative 4/3 and 0. Then we have the part of the number line after 0. So I'm going to make my tentative number line here for x's. So we have negative infinity to negative 4/3. So that's the part before 4/3. Then we have negative 4/3. Then we have between negative 4/3 and 0. Then we have 0. And then we have the part after 0, 0 to infinity. Okay, and what are we looking at? Well, we're looking at the derivative, right? And the original function, what it happens. So what are we looking at? We're looking at when is the derivative positive and when is the derivative negative. So we need to figure out if this first interval, negative infinity to negative 4/3, if the derivative is positive or negative. So I'm going to test a value. What number is in that interval? That would be easy. I'm going to test x equals -2. And what am I going to plug x equals -2 in? To the derivative. So f prime of -2 is 3 times -2 squared plus 4 times -2. And that's going to be a positive number. So the derivative is positive in that interval. Well, if the derivative is positive, what does that mean the original function is? It is increasing, or it's going up. So increasing, or it's going up. What happens at negative 4/3? The derivative is 0. Okay. Between 4/3 and 0, I tested x equal -1 because that's in that. See how that's between negative 4/3 and 0, -1. And I found that the derivative was negative. So if the derivative is negative, that means the original function is decreasing. If your slope is negative, your original function is decreasing. It's going down. That's why your slopes are negative. And then at 0, the derivative is 0. And let's see. From 0 to infinity, I think a good tester value would be x equals 1. That's the easiest thing to do. And it turns out that that is a positive value. So that means your original function is increasing or going up. Okay, now let's look at what happened. We have this kind of situation. Our graph basically looks like going up, going down, going up, right? And where does it change from up to down? Right here at x equals -4/3. here. And when does it change from going down to going up at x equals 0? And if you notice, that would be a max, and that's a min. So right here on my chart, I'm going to put a max. So when you go from up to down, that's a max. And from down to up, that's a min. And if we wanted to find the value of the max, we could find f of -4/3, plug it into our original, plug it into this one, our f of 0. That one's easy, it's 1. So now let's look at the actual graph. And we can see that we do have a local max right there and a local min there. So we have a max and a min. And we can see that the function is increasing, decreasing, increasing. So it did exactly what we thought it would do. General question, what does the derivative represent? Represents slope. What happens to the original function at the zeros of the derivative? It's a max or a min. What happens to the original function on the intervals? Well, it'll either be increasing or decreasing. How does the derivative relate to the function? It is the slope. It tells you if the function is increasing because the slope is positive or decreasing because the slope is negative, or neither, which is a max or min. So the derivative graph tells us a lot about the original function. Let's talk a little bit about something you already know. We already know about these kinds of functions. This is a parabola. What do we know about this parabola? Right here, that's leading coefficient is positive, so we know the parabola is essentially happy. And it has a minimum here at the vertex, right? So this is going to be an absolute minimum because the other arms of the parabola go up forever, right? So this point is going to be the absolute min. It's also a local minimum, right? Locally, it is the lowest point, but it's also globally a minimum or an absolute minimum because when you look at the entire function, it's also a min. But here's the deal. In college algebra or earlier in the year, if we wanted to find the value of that vertex, right, that's also the vertex, we would have to complete the square, we would have to factor and set it equal to 0 to find the zeros, and we could find the vertex, which is in the middle between the zeros. But now that we know calculus, we know that that min occurs. Okay, so if we were going to put a tangent line there at the min, the slope of that tangent line would be 0. So why don't we just find the derivative? What is the derivative of that function? Well, it is 6x minus 12. Remember, the critical numbers of the derivative tell you where the max or min occurs, and those are the zeros and the d and e. Now, there's no place that derivative doesn't exist, but we can find the 0. 0 is 6x minus 12 equals 0. Our slope equals 0 when x is 2. So the vertex occurs at x equal 2. If you want to find the y value of the vertex, you could plug f of 2 into the function and get out the value of -7. Let's see if this coincides with the actual graph. Nope, like down here. Here is the vertex, and it's at 2, -7. And so we didn't have to graph to find that. We could just use calculus really quickly to find the derivative, find the critical numbers of the derivative, and then plug that value into the original function. Why would you want to do this? Well, sometimes graphing it is not as easy as you might think. And sometimes when you find the graph, it is a lot harder to find that vertex. So it is great to know calculus because you can get there quicker. This slide is a summary of what we've already talked about, and there's something key that I want you to look at, and it's this chart down here. I made this chart for you because it's a great way to look at what we know and evaluate it. So when your derivative is positive, that means your original function is increasing. It's going up. When your derivative is negative, your original function is decreasing or going down. And again, positive, increasing. And does there have to be a sign change in the derivative? No. You could have positive followed by positive, and that's okay. You just won't have a max or min between those intervals, and that is totally fine. But if you do have a max or min, let's talk about when that happens. So when your x equals a is a critical number, remember a critical number is when your derivative is either 0 or does not exist, d/e. Okay. But if your function is going from increasing to decreasing, that's how a local max occurs, because you're going up and then you're going down. So right in the middle is a max. Likewise, on the second critical number, you're going down and then up. So that's why you have a local min. So hopefully this chart can kind of help you. And also note over here, local extrema could also be global or absolute extrema. So because it's local doesn't mean it's not also the largest one overall. This next example, the third example, is very similar to the very first example. So this would be a great one for you to test yourself out on and then check your answers. So if you want to, take a minute, write this down, and you're going to find where the function is increasing, decreasing, and local extrema. So in other words, local maxes and mins, you need to find the derivative and find the critical numbers and make a chart. So go ahead and do that, and then you can check your work against my work. See if it matches up. Okay, so what I've done so far is just found my derivative, which is my slope. I got 3x squared minus 12. And then I have to find my zeros and my d/e. There's no place that my derivative does not exist. Now, briefly, I want to talk about this. Because we're not in class, I'm not going to do some of the more difficult examples that you have to find the d/e part. I might do that on the next section, but just know that this is a critical thing to look at. It's just not happening to us. X squared equals 4, which means x equals positive 2 and negative 2. So for my chart, I'm going to have to make my intervals in terms of positive 2 and negative 2. Like here's your number line, here's 0, here's positive 2, here's negative 2. So we got this part, and we got the part in between, and then we got the number line after. So we have this one, and this one to consider. So I have negative infinity to negative 2. Then I have negative 2. Then I have between negative 2 and 2. And we have 2. And then I have 2 to infinity. So for our intervals, we only consider our critical numbers. If I had 3 critical numbers, I would have to do an even longer chart. So keep that in mind. Your chart can get bigger. Okay, so the derivative and the original function. I would probably test here x equals negative 3, and I got that the derivative is positive in that interval. So that means the original function is going up or increasing. Here I tested 0 because that's a nice easy number to test, and I got the derivative is negative. Now remember, when you're testing up here. You're plugging those tester numbers into the derivative, not to the original function, because the derivative is the slope. So if the slope is negative, that means the original function is going down or decreasing. Okay, so what happens right there in the middle? Well, the derivative is 0, but what happens to the curve? It's going up and then going down. So right there is the local max. Okay, what happens at 2 is a 0. Okay, if it was a D and E, I would just put D and E there. And a nice tester is test x equals 3. And if you put that into your derivative, you get a positive value out. So it's positive in that interval, which means the original function is increasing. What happens between? What happens when you go from decreasing to increasing? You have a min. Okay, and if you wanted to find the values, you could plug them back in. So if you want to find the max, it occurs at x equals -2. You plug that into your original function. -2 cubed minus 12 times -2 plus 1. And you get out what? 17? And you would do the same for the minimum. Let's check ourselves against our graph. And it looks like we got it. Here's our max. It's a local max. And here's our min. Okay. For this one, I would have assigned this one as an exit ticket, but since we're so close to the end, I don't want to inundate you with work. I'm going to tell you right away, you're looking for a local min. Okay, you're looking for a local min. So what has to happen for a local min to occur? Well, you have to have some interval. And for a local min, the derivative has to go from negative to positive, because that means the original function is going from down to up. In other words, decreasing to increasing. So you need a sign change of the derivative from a negative to a positive, and that'll be your min, and this will be a critical number. So it could be a 0, it could be a D and E. You are given the derivative right here. So if you're going to find the critical numbers of your derivative, and there's more than one way to do this problem, by the way. To find the zeros, you could graph it and find out when 3x squared plus 4x minus 7 equals 0. And there's no D and E. You could graph it and find when the zeros are. You could solve it using the quadratic formula, everybody's favorite. I graphed it, but I also checked myself using the quadratic formula. And it turns out the answer is A. That's where the local min occurs. It occurs at x equals 1. So I want you to check yourself with this, and you can text me or call me if you need help. You will be very happy to find out that there is no homework for this section. And instead of homework, I'm going to have you do something over this topic on an exam.